Bismillahirrahmanirrahim. Assalamu alaikum. Welcome back to my YouTube channel. And in today's video, we're going to discuss about the atoms and molecules and non-covalent interactions analysis. So basically, until now, we have discussed how to do the QTAIM analysis using multi-WFN and also how to perform the NCI analysis and get its results. Now, the most important thing is that how would you interpret these results and how would you use that data into a publication or a discussion or a presentation, whatever. So we're going to discuss just this molecule. I took this molecule because it has a few different kinds of interactions and I just had its data. So it was easy to follow this. So we'll use this molecule and we're going to discuss it. So what I have done is I have done the NCI analysis and got its NCI, and then we also have its aim data, so all the atom connections and their values. And now we're going to discuss this. So if you want to know how did I get this data, then you should watch the previous videos, as I will mention now in the presentation, and then you can do that yourself. So let's start with the molecule. So here is the molecule, and I have obtained its electrostatic potential map according to the method I have shown in one of my previous presentations. So from the checkpoint file of the molecule, I got this map. So it basically tells you about the regions of more electron density and low electron density. So you can see that these red regions, they are having more electron density, and the blue regions have the least electron density, and the green ones and the yellow ones are in between. So it's obvious that you can see that these oxygens, they've got more electron density on this side. These oxygens, here is an oxygen. And these hydrogens, which are bonded to the carbons that are directly attached to a nitrogen atom, they are quite acidic hydrogens, and the hydrogen on nitrogen itself as well. So this is just an overview of the molecular broader picture, and now we'll move on to its further studies, like the aim and NCI analysis. So what I did is optimize the molecule at a reasonable level of theory. I said reasonable because it's really your choice what level of theory you want or you prefer. And then I used the fcheck file. I formatted the checkpoint file and dragged into multi-WFN and followed the steps as mentioned in these two videos to get the aim and the NCI data from there. And then I would like to introduce or like discuss QTAIM a little bit, so you have a foundation, a basic foundation of how to describe it or what are you going to deal with. So QTAIM is basically a method that looks at the shape of the electron density in a molecule, and then it uses it to define atoms and bonds in an objective and mathematical way, not just based on drawings or intuition like Lewis drawing or such kind of concept. So if you think of electron density as a 3D landscape of hills and valleys, so what we're going to do is, let me convert it to a laser pointer. Yeah, that's better. So consider this is a molecule. These are two atoms bonded together, and this is a molecule. So these are hills, and then these are valleys in between the hills. So these are two hills and then two valleys. And similar, there is a hill, there is a valley, and a little hill, and then a flat surface. So what actually happens is, if you look at the hills and valleys, so you see these hills as the high density regions. So these are the highest points and they have the high density regions. It means that electron density around the nuclei is highest. So these are the tallest. So you get different kinds of the points. And I told you in QTAIM analysis that we use 3 - 1 bond critical points. But you also get 3 minus 3 critical points, and those are called nuclear critical points or NCPs. So NCPs are basically the density at the nucleus is the highest, around the nucleus is the highest. And then you see that as you move away from the nucleus, from this atom and the other one as well, and this is a point which is a saddle point, where you see the density is lower than peaks. It is lower than peaks, of course, but higher than valleys. So these are the valleys. So it's a saddle point where the density is higher than valley but lower than the peak. So this is called a bond critical point. So this, if it lies between two atoms, so it's not necessary that if you find a saddle point that is not between two atoms and you call it a bond critical point. No, if it is between two nuclei, then it will be called as a bond critical point. And similarly, in this case, you see here is the bond critical point. And these regions at the end, they are called low density regions. They are far from nuclei and they are deep valleys or flat points. So this is basically the idea of QTAIM analysis. And now I'm going to show you the real interpretation, which took me a while. So I studied quite a bit of literature, tried to gather all the information into this one table, and just to mention here that it's not an absolute cutoff for QTAM. So there is no absolute cutoff for of numbers like this. So these are all approximate and based on the literature and of experience of different people that that is presented in the literature. So I took these values from literature and I have given the references at the end. You can see here, you will find a slide of references and I'll also put it in the description of the video so you can directly access those papers from where I got all this data. And this is just a guideline. It's not an absolute value. Just remember this point before going further into detail. So if you look at it, I'm not going to waste too much of your time, but it is necessary that we discuss a few basic things. So if you look at the density of all electrons, rho, so we have these different values, rho, Laplacian of electron density, rho, and then kinetic energy, potential energy density, and their ratio. And then I also find an opposite ratio in one of the papers, so I just included it. And then you have the HR, that is the total energy density, the addition of kinetic energy density and potential energy density. So if you look at the rho, if it is equal or greater than 0.15, it is a covalent bond. It is less than this region, it's a non-covalent, and then partial covalent between these regions. Ionic bond is really a trick. I couldn't find it very well isolated in the literature at some point, but somehow I arranged this table as a guideline. So the Laplacian of electron density is negative for covalent bonds, but positive for the other values. Positive mean greater than zero, negative mean less than zero. So in the literature, you can find it in both ways. Like some people say it is less than zero, some say it is above zero, but it essentially it all means the same. And kinetic energy density is mostly positive for everything. But in potential energy density, you will find some trends. For example, for covalent bonds, you will see that the value of VR is generally greater than the GR, and in non-covalent, it's the opposite. So these are all in non-covalent interactions. And then if you look at the ratio, so these two things essentially represent the same concept. And it's just the way of looking at things. So if you do minus G over V, because V is always negative, so minus minus will cancel each other, or you do the absolute value of V divided by G, you still have the same. It's just the opposite, but you have those positive numbers. So if this value is less than 0.5, the bond is covalent, and it's greater than 1, then it's non-covalent. And if it's between, then it's a partial covalent. And similarly, this one, if it is greater than 2, it's a covalent, less than 1, non-covalent. And if it is in between, then it's a partial covalent, or some strong H bonds also fall in this region. And then total energy density is also negative for covalent, but positive for non-covalent. And for partial, it's near to zero or slightly negative. And of course, for ionic, it is also positive. So this is just a basic overview of the concept, how things will work. So now we're going to implement all this into our own study. And then there are a little other things that I asked ChatGPT, and I don't always trust it at the moment because sometimes it just gives you wrong values. But then I correlated this data with the table I had, and it correlates well, not too bad. So it's just another broader guideline for weak and medium and strong H bonds, the value of rho, and then Laplacian similar, and total energy density. It also tells you the strength, and then you can also have a look at the bond length. So this is basically for the hydrogen bonds. And then come back to our molecule. So this is our molecule, and I label the atom numbers, which were discussed here. So if you look at this QTAIM data that I showed you earlier in the Excel sheet, and see that the bond critical point between the oxygen 22 and iodine number 15. So there is a bond critical point over here, and for which, if you look at the density, and then it's Laplacian of electron density and all the other values, and you compare them to that table, they all fit well to a partial covalent bond. So what I should actually do is bring up that table alongside so we can easily see it. Just give me a minute and I'll bring it on. Yeah, here it is, and it looks better, I believe. So if you look at the density of this bond, it tells you that it is where it is. It is actually in this range, 0.03 to 0.10. It's 0.08. So yeah, it's in this range. And then if you look at the Laplacian, that is positive, positive. And then if you look at the GR is positive. So we're going to look at the VR and the HR and the ratio. So if you look at HR, it is negative, and it is slightly negative, 0.02. It's not too negative. So it it comes out to be in this region. And then if you look at the ratio, 0.6. So if it is less than 0.5, it's covalent, greater than 1, it's non-covalent. And if it is in this region, it's partial covalent, or like it is still non-covalent, but it's a bit stronger. So it falls in this region. And then if you look at the distance of the atoms, that also gives you a clue. If you have a bit of knowledge of different bond lengths, you can correlate it. But overall, all these things correlate well to the partial covalent nature of this bond. And then if you look at the other bond, that is the oxygen number 21 and hydrogen number 19. So we only found two BCPs here, while because during the analysis, I took this one as one fragment and this one as the other fragment. But I believe if you take this as one fragment and keep the iodine on the other fragment, then you will also find these BCPs and other data as well. So I'm discussing this one now. So if you look at the 0.01, the density is in this region. And then if you look at the Laplacian, that is positive. Of course, it's positive for non-covalent interactions. And then the GR is positive, and HR is 0.001. It is positive. So it can be in these two regions, like it's near zero, but it is positive. So it is not very clear if you just look at this value. But then if you look at the value of this ratio, it is 1.2. So yeah, it's also in this region. And sorry, I'm looking at this one. It's this one. So it is here, not here. So based on all these different things, you can definitely consider this as a non-covalent interaction. It's like a weak hydrogen bond. Of course, it looks like a hydrogen bond. Otherwise, I would call it a van der Waals interaction, but it is a weak hydrogen bond because it's a hydrogen that is hydrogen bondable, and then the next atom is an oxygen. So it's very clear. So have you seen that how on the basis of all this information we can conclude about the nature of the bonds? And now we move on to the NCI analysis. What is NCI? It is basically a way to visualize weak interactions between atoms or molecules, and that are not covalent bonds. So there can be hydrogen bonds, pi-pi stacking, van der Waals, steric repulsion, these kind of interactions. So you can think of NCI as a map of where atoms feel each other without forming real bonds. So it is, yeah, where atoms don't form bonds, but they feel each other. So that feeling is the interaction that is called non-covalent interaction. And it takes the electron density of the molecule and look for regions where the density is low. So it is not a covalent bond, but the density changes slowly, indicating something is happening there. If the density changes too fast, then it's not a bond. It's very far. So these regions are the non-covalent interactions. And then you will see different color schemes. If it's a blue color, you'll see strong attractive interactions. That is a hydrogen bond or a halogen bond. And then if it's green, it's weak dispersion interactions, van der Waal, pi-pi stacking, etc. And if it's red, it is a repulsive interaction or a steric clash. So now we're going to use this value on our molecule, and this plot I got from the NCI analysis. And then I also put the same QTAIM table here so you can directly compare things. So if you have a look here, this was a kind of a polar covalent bond, sorry, partial covalent bond. And this was a weak hydrogen bond, or you see that it fills fire, it is in the range of van der Waals interactions. And then there is some repulsion because of this lone pair on oxygen atoms and the bigger size of the iodine atom. And then it also shows you another interaction here, which was not shown by the QTAM. So if you include iodine as a second fragment while analyzing QTAM, then of course you will also find this PCP as well. So this way you can say that the NCI plot actually supports your claims of the QTAM. And now we move to the reduced density gradient. Reduced density gradient is a mathematical function that tells you how quickly the electron density changes in space. And if you look at super simple terms, if RDG is small, the electron density is flat or smooth. This usually means a non-covalent interaction region like this one, this small. But if RDG is large, the density sharply changes, usually empty space, no interaction. So if it's like this large, it means that there is no interaction. So you have to basically look for this small changes or interactions. So yeah, RDG is a way to find interaction regions, and then you can see that there are different regions, like hydrogen bonds are appearing in this region, and then near to zero you will see the van der Waals interaction, and to the right, to the positive side, you will see the steric effects. So yeah, it is an extension of the M theory for visual study, and these spikes you can use them in the same color scheme as we discussed just before. And the NCI checks basically if an interaction is attractive, like these ones, repulsive, or weakly attractive. So these are the regions where you have to look for. And the x-axis tells you the sign lambda to a fro. And if it is negative, these are attractive interactions. If it is near zero, it's weak van der Waals. And if it is positive, it's steric interactions, repulsions. And y-axis is the reduced density gradient, which if it is small, it's interactive regions. And if it is large, there is no interaction. So you have to keep these things in mind, and then you have to look here that you can find the van der Waals, and you can, of course, find some repulsive interactions here as well. And these are weak attractive forces present. And there is some hydrogen bonding, of course. You can see that there are hydrogen bonding interactions as well, which, of course, are here and here. So overall, all these things support each other, and they give you a sound understanding of the concept, and then you can write up about this. So you can give that table into your paper, you can give these figures, and then you can describe all these things based on the facts, and then you can give the literature references to support these claims. So yeah, here I made just a table to discuss like what QTAIM and NCI can do and what cannot do. So it's basically, yeah, I'm not going to describe or discuss this table into detail. It's just for the information. You can have a look yourself. So what QTAIM, NCI, and RDG have specific, what they have in common, and what each other has as a difference. And then, yeah, here are the references that I have used to find out the value. So many of these references are Professor Bader's original papers, who is the founder of these interactions. And then, yeah, we should be thankful to these guys, the author of multi-WFN as well, which is freely provided, so you can easily use it. And then, yeah, I will put all these references into the description of the video, and you can copy them. Then you can use this table on your own, or if you want to modify, if you study more literature, you can modify it according to your needs. And if you have any questions, you can post in the comments, and I'll try to get back to you as soon as possible. Thank you very much for watching. I hope you enjoyed it, and we'll see you sometime in the next video. Thanks. Bye bye.